So in this lesson, we're going to expand on the idea of directional derivatives and expand it to something that's really actually very important, which is called the gradient, or grad of f. And so what we get here is here's our definition. It's let z be f of xy, and it's a function of x and y, such that fx and xy exist. And the vector called grad f of xy is called the gradient of f, and is defined as grad of f of xy equals the partial of f with respect to x, xy, I, plus the partial of y with respect, the partial of f with respect to y, xy, j. All right. So basically, what it is it's a vector made up of the partials of f of xy. And you can actually also we can expand this, right? We can in fact expand grad of f of xy to include also, say, f of xyz, and that would then be the partial of f with respect to xi plus the partial of y with respect to j plus the partial of z with respect to k. Or we might actually just write this as fx, fy, fz written as a vector. Or if we're doing two-dimensionally, we might actually write this as fx, fy. Okay, and that's your gradient. The reason why we're actually going to write out something as the gradient in this form is because sometimes what we're going to want to do is we're going to want to actually do a lot of those things like the dot product or the cross product of different things. Like we're going to want to work in vector calculus with these ideas of directional derivatives. So all that stuff that we've done, functions of several variables, all the stuff that we've been doing, we have this vector way of working with those things as well. And so the gradient actually plays a big role in doing that. By the way, this little symbol right here, is called a del. All right. Although we generally, if it's in front of a function, it's just going to be called grad f of xy. Okay. So that's what the gradient is. So suppose that we have an example now, and we'll have f of xy equal x squared minus xy plus 3y squared. Okay, so grad of f, which is how we're going to write this, is going to then equal, we're going to get 2x minus y, I plus, and then this will be negative x plus 6y j. Okay, notice this is fx, this is fy, and there is the grad. Now let's say, for example, I take f of xy is equal to sine 3x cosine 3y. Then grad of f is going to equal the derivative with respect to x, which is going to be 3 cosine 3x cosine 3y, I plus, and then we'll take the derivative with respect to y. So this is going to be negative 3 sine 3x sine 3y. And there's our gradient. Okay, so finding the gradient, not such a bad thing. We're going to talk a little bit more about what exactly it is. It's going to come in actually quite handy when we're like looking for tangent lines or looking for normal curves. So the gradient is going to come in handy for us when we want to actually have like an alternate definition of our directional derivative. So if you remember, we had like the directional derivative du of f of xy. It ends up equaling fx and what u1 plus fy u2, where u1, u2 is that unit vector, right? So that's the unit vector for our direction. And what you want to notice is that this actually is the gradient dotted with u. Okay, so if this is u, this is the directional derivative du of f of xy is actually equal to the gradient of f dotted with u, which is our direction vector. Okay, and the great thing about this is that we can actually, if we did it in 3 dimensions too, du, say for example, of f of x, y, z, is also going to be the gradient of f dotted with u. Just that our gradient now is going to be ijk. It's going to be a vector of ijk. And we'll still, though, dot it with u, dot it with our direction vector. Okay, so the gradient ends up becoming, or these two equations end up giving us ways to actually find our direction vectors, or our directional derivative, excuse me. So let's take an example. Let's suppose we want to find dv f of xy for v equals 3/8 for f of xy equals sine 3x cosine 3y. So remember that we're going to need a unit vector, u, which will equal v divided by the magnitude of v. So that's going to end up being 3/8 divided by the square root of 3 squared plus 8 squared, okay, which is the square root of 73. So this is going to be 3 over root 73, comma, 8 over root 73. And we actually, in fact, already found fx and fy. So our gradient, grad of f, is going to equal, once again, we're going to have 3 cosine 3x sine, cosine 3y. And negative 3 sine 3x sine 3y. Then we'll take the dot product of those two, so that we're going to take the gradient of f dotted with u, and so that's going to end up equaling 3 root 73 times 3 cosine 3x cosine 3y plus plus 8 over root 73 times negative 3 sine 3x sine 3y. And simplify, that's going to end up being 9 over root 73 cosine 3x cosine 3y plus 8 over root 73, or excuse me, minus 24 sine 3x sine 3y. And there is the directional derivative. There is dv, actually this was a v, wasn't it? dv, or excuse me, actually du, we changed it to u. So du fx, which equals the grad of f dotted with our unit vector. And there it is. That's how we utilize the gradient in order to find our directional derivatives. So one of the handy things that we can do with the gradient is we can go out and maximize or minimize directional derivatives. So now if you remember, we've got du of f of xy is going to equal delta, or excuse me, del f, or grad f dotted with u. Now remember, u is a unit vector, and also if you kind of remember from earlier, we know that what this is going to be is the magnitude, okay, of del f, or excuse me, of grad f, times the magnitude of u, okay, times cosine phi, okay, and phi is, this is the angle between u and grad f, right? So remember that we have that equivalency here, okay? And so what we want to do is we want to think to ourselves, okay, well, when is that going to be at its biggest, all right? So remember that cosine phi, whatever phi is, okay, has got to be greater than or equal to -1 and less than or equal to 1, okay? Cosine phi will equal -1 when phi equals pi, right? Okay, and cosine phi will equal 1 when phi equals either 0 or 2 pi, right? Actually 0, right? Okay, just if you think about it, 0. And so if I think about this, well, a couple things in here that, remember the magnitude of u, so these are two facts that we have, then the magnitude of u is going to equal 1, right? Okay. So if I look here, this directional derivative is going to be at its maximum when cosine of phi equals 1, right? Okay, because that's as big as cosine of phi can possibly be. Well, let's think about what that means. All right. I've got, here's my xy plane. And what I want to do is I want to say, okay, so there's that direction, right? That's when phi equals 0, all right? And so what that means is that the direction of u and the direction of grad f are going to be in the same direction. They're actually in the same direction, and they're pointing towards each other. So there's 0, okay? 0 is the angle between them. So basically, the directional derivative, du of f, is maximized when u and del f are in the same direction. Okay, so that's first thing that we want to get there. Hey, that's kind of cool, right? When phi equals 0, and that means that del f is in the same direction. Now, if I take this, move it differently, just a little bit differently. If I look here, when is phi going to equal pi? Well, there's this. So the angle between the two of them is now 180. So basically, if this direction is u, then that means this is del f. Okay, so when they're pointed in the opposite directions. So when del f, or grad f, excuse me, is in the opposite direction of u. Or what that basically means is that we basically our del f, okay, equals some scalar or a negative c, some negative scalar times u. Okay, and del f is maximized when we have del f equals some scalar times u. That is that they're in the same direction, right? They're scalar multiples of each other if they're in the same direction. So opposite directions minimized, and same direction is when they're maximized. In addition to that, if we go up in here and we look at it, what you're going to see is, remember, this is equal to 1, because that's a unit vector. Cosine phi is whatever it is. In fact, it'll be 1. If it's maximized, it'll be negative 1 if it's minimized. So what that means is that the maximum value is just going to be the magnitude of del f. So the max will equal del f. And it will happen when it's in the direction of u, okay? And the min, okay, will end up being negative del f. Negative the magnitude of del f, excuse me. Right? Because it's now in the opposite direction of u. Okay? And so that's its minimum value. So this actually gives us the properties of the gradient. You can write these down. This is basically what we just said. So if del f of x of y equals 0, right? So then the directional derivative equals 0 for any vector u. Okay? So basically what that means is that if the, kind of the sum of the directions in x and y are equal to 0, then, you're not going anywhere. It's a 0. Now, if the directional derivative, if the gradient does not equal 0, then the directional derivative of f is maximized when u points in the same direction as del f, and the maximum value of the directional derivative is just equal to the magnitude of the gradient. Conversely, the directional derivative is minimized when u points in the opposite direction for the gradient, and so the minimum value of the directional derivative is the negative magnitude of the gradient. Okay? And so we can utilize this and actually, in order to figure out what the maximum directional derivative is, right? And so this is one thing that actually can kind of come in handy if we want to know what the maximal rate of change is for a particular surface at a particular point. So let's consider this question. Let's find the direction for the directional derivative of f equal to 3x squared minus 4xy plus 2y squared at negative 2, 3 as at a maximum. And then what is the maximum value? So what we're looking for is the vector u, okay, that's pointing in the same direction as f of xy, or as the gradient of f. Okay, so remember we need u, right, same direction as grad f. And in this case, it's grad f at that particular point. Grad f, negative 2, 3. So let's do this. Let's find fx or the partial with respect to x, so that's going to end up being 6x minus 4y. And fy is going to end up being negative 4x plus 4y. Now, fx at negative 2, 3 will then equal 6 times negative 2 minus 4 times 3. So that's negative 24. And fy is going to equal, or fy at negative 2, 3 will equal negative 4 times negative 2 plus 4 times 3. Okay, and that ends up equaling 4. Or excuse me, not 4, but 20. Pardon me. So that's 8 plus 12, that's 20. So the gradient of f at negative 2, 3 is equal to negative 24, 20. Now we want u to be in the same direction as the gradient of f at negative 2, 3. So I'm just going to actually turn u is just unit. So we're going to get u is going to equal negative 24, 20. And then we'll divide it through by the square root of negative 24 squared plus 20 squared. And so this ends up giving me negative 24 over, and this will be 4 root 61. Okay. Comma 20 over 4 root 61, which is just equal to negative 6 over root 61 and 5 over root 61. And so that's the direction. I mean, obviously the direction is also negative 24, 20. So it's going to be in the u is essentially going to be the value of the gradient. That's your direction. Now we need to figure out what that maximum value is. Well, remember that the maximum value is simply going to be the magnitude of the gradient. Okay, so the magnitude of the gradient, and so that's going to end up being the magnitude of grad f is going to equal, well, we saw it before, it's going to be the square root of negative 24 squared plus 20 squared, and that actually ends up equaling 4 root 61. Okay? And so that's how you go out and find the maximum. To find the minimum, if we want to find the minimum, our min would go in the opposite direction. So it would in fact go into u equal to 6 root 61 comma negative 5 root 61. So that's the exact opposite direction. We just multiply u by negative 1. Okay? And the min would then also be negative grad f, which equals negative 4 root 61, and that would give me my minimum. Okay? So hopefully that kind of displays how it is that we'd actually go about finding these minimums or maximums.